Okay, now we're going to look at complex numbers, and we're going to start with a little bit of review here. So how do we solve this for x? Remember, this is an equation. It's an equal sign, so we're going to solve for x. Yes, we could factor this, but we're going to just do the thing since x only appears once. Whoops. We are going to isolate the variable. So we are going to add 4. Oh, it's over here. Sorry, this is a different app I've been using for notes. So we're on eraser. Okay, so we're going to add 4 to both sides, and we're going to get x squared equals 4. These cancel. 0 plus 4 is 4. Then I am going to square root both sides, and we're going to get x equals, and remember now when you square root, it's plus or minus 2. So remember, that's 2 solutions, and 2 squared is 4, and negative 2 squared is 4, so that's why that's our solution. We've known how to do that for a long time. That's nothing new. The new stuff this year is when we do this one. We're going to, let me see here. I want to make it a little, oh, that's annoying, sorry. All right, how about if that's what I wanted to do. All right, if I subtract 4 off both sides, I'm going to get x squared equals, oh, I have to change the setting for each time. No, that's good, okay. X squared equals negative 4. Then I square root, and this is the new stuff. Square root of x squared is x. When I square root a number, I get plus or minus. When I square root negative, we can't square root negatives because no number times itself gives you a negative, except if you use imaginary. So the square root of 4 is 2, and because we're squaring a negative, it's I, and those are our 2 solutions. Remember, 2i times 2i, I just want to prove to you that it's negative 4. 2i squared, or 2i times 2i, is 4i squared. And then I squared is negative 1, so that's equal to negative 4. So when you square 2i, you actually get negative 4. And then, of course, if you square negative 2i, if you make both of these negative, when you multiply a negative times a negative, you get still positive 4i squared, which is negative 4. So there's those solutions. Then we had some in this form where the order of operations was a little different, and we had to be careful. So first we're subtracting 4. Here they cancel, and I'm left with x plus 2 squared equals negative 4. Now, before I can subtract the 2, I got to first get rid of this squared. So I'm going to square root both sides. I'm going to get x plus 2 equals plus or minus, because I'm square rooting a number. And then the square root of 4 is 2, but then since it's negative, it's 2i. And now I can then subtract 2 off of both sides, and I get x equals, and now I have a real number and an imaginary number, and so I'm going to write them. I can't add them together, so I'm going to write them in that complex form, a plus bi. And remember, a is the real part and I is the imaginary part, and that's a complex number. And plus or minus means there's actually 2 answers here. I just want to make sure we recall that. The answers are really 2 different numbers. And those numbers have a special name. They're called conjugate pairs. And whenever you find solutions to equations, the conjugate, if you know one of these is a complex number is a solution, then its conjugate pair is always also a solution. Okay, so real numbers and imaginary numbers, just to review. Real numbers are things like 2 that we saw before, 4, 1/2, square root of 5, pi, negative 7. Okay, those are real numbers. Imaginary numbers are the ones that have I, 2i, 4i, or a square root of a negative. All right? You put those together, and we have complex numbers. That's like all the numbers there are. Those would be complex numbers. So over here, an example of a complex number would be 2 plus 3i. And we can even graph these numbers, right? Our real numbers are graphed on a number line. Right? We know that here is 0, so maybe pi is right here. Maybe negative 7's down here. Okay, maybe 1/2 is right here. They all fit on this number line. So imaginary numbers, we can't use a number line. We have to use a number plane. Imaginary numbers have a real part and an imaginary part. So now we have to plot our numbers on a two-dimensional plane. So the number like 2 plus 3i, I'd go over 2 on the real axis, and I'd go up 3 on the imaginary axis. And that's how you would plot the point or the number 2 plus 3i. Okay? So that's a complex number. It should always be written in the form a plus bi, where a is the real part, which we graph, or we can use the real axis for, and I is the imaginary part. Okay, so add and subtract. So we've done a bunch of this. This is just review. This is not multiplication, so we have 4 minus 3i. We distribute the plus 1, plus 7, plus 9i, and now we can add the i's together and add the real parts together. So 4 plus 7 is 11, and then this is plus 6i. So that's our complex number. It is complex, and we always write the real part first. All right, let's do this one. 4 plus 5 minus 12i, so 4i. So I'm going to do 4i plus, I'm going to distribute that positive 1, so it just becomes this. I'm multiplying a 1, which doesn't change anything. Now I can add these imaginary parts together. The real part is 5, and then 4i minus 12i is negative 8i. Okay, now we're multiplying, so we're going to distribute. And we get 4 times 3 is 12, and then 4 times 5 is 20i, and that's all we can do. We can't add reals and imaginaries. Over here we've got 3 times 3 is 9. It's going to be plus 21i, and then minus 6i, and then minus 14i squared. So in here, this is the interesting part when we simplify this. We get 9. That's our real part. Now we can combine these imaginary parts. 21 minus 6 is 15i. But then minus 14i squared becomes plus 14. This is a real number, and it came from multiplying two imaginary numbers. Whoops, I should probably circle the sign as well. I multiplied these two imaginary numbers together, and I got a real number. So imaginaries are not closed under multiplication. All right, so anyway, I squared equals negative 1, and that's the whole key. So this is really negative 14 times negative 1, which becomes plus 14. So now it's real. I can add it with the other real part. So I get 23 plus 15i. All right, moving on. If we want to factor these, so now I know that this is difference of two squares. Okay, just a review. You put the square root of the first guy in the first slot. You put the square root of the second guy in the second slot. So like if I square root x squared, I get x. If I square root 4, I get 2. And then you make it a conjugate pair, plus and minus 2. So that's how we factor that. We had said you can't factor a sum of two squares. You can only do it if it's subtraction, right? Well, now we have addition here. Now we can do that because we can call it x and x, and we know it's plus and we know it's minus. The reason we need the plus and the minus is because there is no x term. It's like a plus 0x in the middle. There is no x term, so I need the middle parts to cancel out. So I'm going to put 2 and 2, and I'm going to use I, and we'll see what happens here. So when you have x squared plus a number, you could do difference of two squares again, but these are going to be imaginary numbers. I'm going to multiply it back out just to show you what happens. X times x is x squared. X times negative 2i is negative 2xi. That's an imaginary number. Now I'm going to distribute the 2i. 2i times x is plus 2xi. And then 2i times negative 2i is negative 4i squared. So now the middle parts, that's what I was talking about here, right? When you multiply the outsides and then you multiply the insides, those are going to cancel out because you have a conjugate pair. You have the plus and you have the minus. That's what's nice about conjugate pairs. When you multiply out conjugate pairs, you don't get a trinomial. You get a binomial. So these will cancel out, and I get x squared minus 4i squared. So you get that negative number because when you multiply a positive times a negative, you get a negative. But now because you had i's there, remember that I squared is equal to negative 1, and negative 1 times negative 4 equals x squared plus 4. So the moral of the story here is you can now factor a sum of two squares. You're just going to have imaginary roots. So you got to put an I in there. So it's going to factor just like the other one, x squared minus 4. All right, so here, let's try it again. If this were x squared minus 36, it would factor by difference of two squares into x plus 6 and x minus 6. But I need it to be a sum of two squares, so I'm going to put imaginaries in there, and it's going to work out. So now we know how to factor this type of thing. Okay? Moving along. How do we divide? Well, when there's just one term, a monomial, on the bottom, we can distribute division just like we distribute multiplication. We can divide each part of the numerator by 3. So then that will simplify to 4/3 minus 1i, because 3 divided by 3 is 1. Okay, we're going to use that a lot when we start doing the quadratic formula in our next lesson. So that's going to be an important skill right there. You have one term on the bottom, you're going to distribute that division, okay? And then we're just looking at solving again. So let's see where this brings us. There's some moves in here that'll be interesting. So I'm going to subtract 1 from both sides. Whoops, that's a minus. Where's my eraser? Thank you. Minus 1 squared, and that'll be negative 27. Now we're going to square root both sides, and we're going to get 3y minus 1 equals plus or minus the square root of 27 is going to be some type of I. I can't square root 27, but I can break it up. So I'm going to do the positive 27 over here on the side, little side mission. That can break up into square root of 9 times the square root of 3. So the square root of 9 is 3, and I can't square root the 3 anymore. So it's going to be 3i root 3. The I was because that negative under the square root, and then I can just deal with the positive over here. All right? So now I'm going to add 1 to both sides, so I get 3y. If I add 1 over here, it cancels. I'm going to add 1 over here. I get 3y equals. I can't add an imaginary and a real, right? I wish I had this is, like I said, I haven't used this app before. I wish I had like a highlighter. I mean, not a highlighter, but a laser pointer thing. So this number up here is imaginary. This number is real, and we can't add them together, so we just write it as a complex number. 1 plus or minus 3i root 3. And remember, that's actually two numbers, 1 plus and 1 minus. Now, lastly, I divide both sides by 3. You have to divide the entire side by 3. You could leave it like this if you like. Let me show you what else you could do. That division, you could distribute the 3, the dividing of the 3 to both terms. This plus and minus separates the top into two terms. So I could say 1/3 plus or minus 3 root 3 over 3. Why would I do that? Well, because now I can do 3 divided by 3 is 1. And I could say plus or minus root 3. That's a simplified version of this. I don't know. That's for you to decide, I think. All right. Conjugates. So what if we're dividing by an imaginary, right? So this was if we're dividing by a real. What if we're dividing by an imaginary or a complex number? What you're going to do is you're going to multiply by another I because you want that real number on the bottom. So we're going to multiply by the same thing. We're going to multiply by 2i. We're going to multiply it by the conjugate pair. If it's only one term, we're not going to worry about conjugates. We're just going to multiply by the thing itself. If what we're dividing by, this 2i, is a monomial, just multiply by itself. And you have to multiply by the same thing on top because this fraction is equal to 1. And when you multiply by 1, it doesn't change the value. It might change the look of it because this is a weird-looking 1, right? This is a weird 1, so it's going to change how it looks, how the original thing looks, but it won't change its value. All right, so on top, I have 2i times the entire numerator. I'm just going to write that out for a second. And on the bottom, I have 2i times 2i. I'm just writing out what I'm doing. So then I distribute, and I get 8i minus 6i squared on top. 2i times 2i is 4i squared on the bottom. All my I squareds turn to -1. So I have 8i minus 6 times -1 instead of I squared, over 4 times -1 instead of I squared. So it becomes 8i plus 6, and I can't add those together because I have imaginary and real. And then over -4. We typically like to write our complex number as the real part first, and then the imaginary part over 4. And then, again, simplifying here and dividing, I noticed that a number divides into all of these, right? So I could distribute my division to each part of the numerator, so I could call it 6 over 4 plus 8I over 4, and then simplify those fractions. 6 over 4 is 3 over 2. 8 over 4 is just 2I, and I could leave it like that. I'm going to tell you when we start doing quadratic formula, think of this as 2 terms up top, 1 term on the bottom, and if there's a number that divides into all of them, you can go ahead and do that. Like I noticed 2 divides into all of them, so I have this would be a 2, this would be a 3, and this would be a 4, and that's basically what we have going on there. But then you break it up and you get the 2I, so I don't know. There's multiple ways that you can simplify that. We're going to just work on that as we go through the practice. This stuff will come up. Okay, here's the big one for today. We want to multiply by the conjugate pair in the denominator. So what is the conjugate pair of the denominator? We don't want the imaginary numbers in the denominator anymore, by the way. The goal is to turn this imaginary number or complex number in the denominator into a real number. That means eliminate the I. So the way you do that is you have to multiply by the conjugate pair, because up here, somewhere we multiplied by a conjugate, didn't we? Where was it? Oh, up here we were doing it. When you multiply by a conjugate pair, what happens to the middle parts? And those are the imaginary parts, right? They cancel out. And then you're left with a real number, okay? No imaginary parts in it. So that's why we would decide right here to multiply by its conjugate pair. So I'm just going to write this out for a second. 4 minus 3I in the top multiplies by 3 minus 2I. In the top, we have to multiply by the same thing because we need this number to be equal to 1. All right, so that's what we do on top. And on the bottom, we got 3 plus 2I times its conjugate pair. So in the numerator, we'll do our distributive property. 4 times 3 is 12. 4 times negative 2 is negative 8I. Now we're distributing the negative 3I, so I get negative 9I. And then plus 6I squared over. And the bottom, we get 3 times 3 is 9. 3 times negative 2I is negative 6I. And then we got 2I. I'm going to distribute that. It's going to be plus 6I. And then that's going to be minus 4I squared. We're going to change our I squareds to negative 1s. So 12 minus, oh, and we can add our i's together. So that'll be negative 17I. Notice the i's didn't cancel out on top because these are not conjugate pairs of each other. So I still have the I in my answer. And then minus 6 because I squared is negative 1, and negative 1 times 6 will be negative 6. On the bottom, I've got 9. Now when I add my imaginary parts together, oh, what happens? They equal 0. So 9 plus 0 is just 9. And that's because they were conjugate pairs. And then we have plus 4, because 4I squared is, negative 4I squared is negative 4 times negative 1, which makes a plus 4. Now on the top and on the bottom, we could add our real parts together. 12 minus 6 is 6, minus 17I. 9 plus 4 is 13. There we go. And that's going to be it. I'm not going to divide this one. I'm not going to distribute the 13. I'm not going to say 6 over 13 minus 17I over 13 because none of these reduce. These fractions don't reduce, so I don't think that's more simple. I like to leave it how it is. All right, so you can try it. I think what's better is we'll probably do these in class as a warm-up when you get to class to kind of talk through some of this stuff. This will be what we'll do in class, all right?